Now we want to talk about internal resistance of a cell. Now, if you have a direct current circuit such as this, a direct current circuit such as this, you see, present the cell, this is a conductor, this is your key, maybe this is your node, it's like a bulb. This is an example of a direct current circuit. I can draw like a cell, a presentation of a cell, a big cell, like a battery on my arms. Now, if you have a direct current circuit, your cell or your battery you are making
use of was designed to provide a specific amount of EMF, to provide a specific electromotive force, which is the electric pressure for charge to flow in the conductor. Like this one, man, it has a EMF of 1.5 volts. But the truth is that
when you have this connection, this circuit, the potential difference across this circuit is not at 1.5 volts. The potential difference when connected to this circuit, the potential difference across this end when connected to this circuit will not be less than 1.5 volts. It is no longer equal to the EMF of which the cell is designed. It's not lesser. They designed this battery to be the EMF, the electromotive force to be what? 1.5 volts. The electromotive force to be what? 1.5 volts. But when it is connected to a direct current circuit, the potential difference across the ends in this circuit will not be less than 1.5 volts. Tell me what you are getting. Now, why is this so? It is because the quantity of charge moving in this cell is being opposed within. Why is this happening? Somebody will say it is the enemy within. Let me say that again. Why is this happening? Because the quantity of charge moving through the material of the source encounters an opposition. Because the quantity of charge moving through the cells, there is an opposition within. So as the charges are moving around the circuit, there is still an opposition inside the cell that oppose the flow of what? Charges. That's what makes the potential difference across the cell in the circuit not be equal to what the cell was designed to give. So that's opposition or flow of charges within is what we call as internal resistance of a cell. Internal resistance of, it is denoted as small letter r. Internal resistance of a cell is the opposition. It's still the same thing as resistance, but it is the enemy within, the resistance inside the cell, the resistance that you can find within the cell, making the cell not to be able to supply its full potential. So the EMF will not be, the potential difference across the cell in the circuit will not be less than EMF. It is just the same thing as resistance, only that it is inside the cell. So internal resistance, which is denoted as R of a cell, is the opposition. You have already knew that resistance is opposition. Opposition of current flow offered by chemicals. When we talk about cell, you see that as a result of conversion of chemical energy, you have electrical energy from cell. Offered by chemicals at between the poles of the cell. So internal resistance of the cell is the opposition of current flow offered by the chemicals between the poles of the cell. Your opposition of flow of charges offered by the chemicals between the poles of the cell. Now you already know what EMF is. You already know what EMF is. As we zoom into this further, you can have a diagram such as this nature. So I'm just zooming into it. This symbol represents what? A resistor. Why this symbol represents what? A cell. Now, resistor, as we know, provide a known amount of resistance. It's designed to provide a certain amount of what? Resistance. But inside this cell, if you zoom further, it also has its own resistance. That's what we call internal resistance. So So there's not that there's a resistor inside it, but it's like there's something like a resistor, but it has all resistance inside. So if you just try to imagine that there was a resistor inside the what cell, that's what I'm labeling with dots. This one now provides internal resistance, while from the resistor you have external resistance, which is denoted with small letter R, and internal resistance is denoted with small letter R. So your resistor will provide you with external resistance, the normal resistance, which will denote with R, big letter R, while internal resistance, the enemy within, they will provide a resistance inside coming from inside the cell. The internal resistance of the cell is the opposition or current flow offered by chemicals between the poles of the cell. Now you earlier knew what a EMF means. You earlier knew what EMF, electromotive force, mean. But now that you also know you are bringing internal resistance of the cell into the picture, we want to revisit the definition again, because EMF is concerned about internal resistance. Once again, this battery, for example, was designed to provide EMF of 1.5 volts. But if you connect it to the electric circuit, it will not provide that potential difference across its end. There is something opposing the charging flow within the cell, the enemy within. So EMF is not concerned with internal resistance. For that, we want to define EMF of a cell again. EMF of a cell as the potential difference across the terminals of the cell when it is on an open circuit. The EMF of the cell is the potential difference across the terminal when it is in an open circuit. So you just have this battery, you want to define EMF, and you have internal resistance at the back of your mind. It is just the potential difference across these terminals when it is in an open circuit. Because you can say this is in an open circuit now, because there's no complete flow of charge. Or this is just a battery to illustrate what I'm holding. The potential difference of the EMF of the cell is the potential difference across the terminals when it is in an open circuit. You have the EMF directly here. Now, you can open the key. This is the same thing now. The EMF of this cell is the potential difference across its terminals when it is connected in an open circuit. You just have the EMF, the electromotive force, the electric pressure which the cell is designed to give. The way it's designed. So let's write it. The EMF, which we denote as E, is the potential difference across EMF of the cell is the potential difference across its terminal when it is connected in an open circuit. When it is connected in an open circuit, that means it is not supplying current to an external circuit. That is, not when it is not supplying current into the external circuits. I believe you are with me. Now, if you don't want to define EMF of the cell this way, there's still another way, based on your knowledge, your understanding. The EMF E of a cell is the work done, as we have earlier defined EMF, is the work done, but this time you are keeping internal resistance in mind. The work done in moving a column, which is the unit of charge, a column of one charge through the external, through both the external circuits and internal and inside the cell. So the EMF of the cell is now the work done in moving a column of one positive charge through both the external circuit and inside the cell. So the work done for you to move a column of positive charge around the external circuit. There is resistance in the conductor and there is resistance in the resistor. So that work done moving a column of positive charge around its external circuits. Not just that. So get that with the work done in moving that positive charge inside the cell because we know there is internal resistance inside the cell. So when we move a positive charge of one coulomb, both in the external circuits, everything here, or together with the load, and inside the cell. So if you want to really get EMF of a cell, the way it's designed, you have to look at the EMF across the external circuit together with the potential difference inside the cell. Summing it up will now give you the original EMF of the cell. And that is why we have this formula. EMF, which you denote as E is equal to V, capital letter V plus small v. A is equal to big V plus small v. So E is equal to big V plus small v. E is equal to big V plus small v. That is to say, to get the EMF of the cell, you have to add big V to small v. But what is big V? Big V is just the potential difference across the external circuits. Big V is the potential difference across the external circuit, or big V is the potential difference across the external resistance. The potential difference across the external resistance. This big V is also called the terminal potential difference. Now, what is small v is now the potential difference across the internal resistance. So now the potential difference across the small resistance, and it is called the lost voltage. Can be called lost potential difference, but it's usually mostly called lost voltage. Why is the reason? Because the internal resistance takes away some of the voltage inside the cell. Look at the EMF. It's supposed to be the EMF of the cell. But the internal resistance, there's a potential difference across the internal resistance that are taking part of the EMF of the cell. And that is why it's called the lost voltage. Because you don't use it to do anything. It is from inside the cell. It is lost. But while the rest of the potential difference is now used to push other charges around the circuit. Once again, big V is called terminal potential difference. What is small v is called the lost voltage. And as we know from Ohm's law, we said that V is equals to I arrow. Potential difference equals to current times resistance. Now this can be we can modify this to now become E is equal, instead of big V, now the I big arrow, because it's coming from the external circuits, external resistor plus this, you see the I arrow, big letter I and small letter arrow, because the potential difference inside the internal resistance. But we are using the same I, that is to say I is the current flowing in the external resistor. We are using the same I, but we use different arrow. The reason why we use the same I because the current that is flowing in the external resistor is also the current flowing within the cell. So we are using the same I because this V are sent to this from Ohm's law. And V is equal to I arrow. The I is the current flowing to the external resistor, and arrow is the external resistance of the external resistor. While I, the same current that is flowing in the external resistor or the conductor is also flowing in the cell. That's why we use the same I. But because we are talking about potential difference cross arrow, the arrow will not be the small arrow, which is the internal resistance of the cell. Now you can modify this one to become E, make I, collect items, factorize I rather. Because you add I on both sides, become arrow plus arrow. Now you can divide both sides by arrow plus arrow over arrow plus arrow. This arrow plus arrow will strike out this. And you are left with E is equals to E over arrow plus arrow equals to I. Because it's an equation that can be written as I is equals to E plus arrow, which is also essential. I is equals to EMF over big arrow plus small arrow. Once again, the big V stands for what? Potential difference across arrow. And the small v stands for potential difference across the small arrow. And that is that. Big V is also called terminal potential difference, and small v is also called lost voltage. It's also called lost voltage. Now, we want to define this terminal potential difference. Terminal PD is defined as the potential difference between the terminals of a cell when it is delivering currents to an external circuit. When it is delivering current to an external circuit. So terminal potential difference is defined as the potential difference between the terminals of a cell when it is delivering current to an external circuit. It is the potential difference between the terminals of a cell. Potential difference between the terminals of a cell when it is delivering current to an external circuit. So you are just paying attention to only potential difference in the external circuit. You are not concerned about the potential difference across all letter arrows. Terminal potential difference is defined as the potential difference between the terminals of a cell when it is delivering current to an external circuit. What we want to now do is we want to play with everything we have not done with our knowledge. Because we said the EMF that the cell is designed with, when you connect it to a closed circuit, it will not be potential difference across the cell. It will not be there. The potential difference across the cell in that closed circuit will not be the same thing as the what? EMF in which the cell is designed, because there is an internal resistance inside the cell. There will not be potential drop inside the cell, which is called lost voltage. But together you add the lost voltage with the terminal potential difference, you will get your total EMF in which the cell was designed for. So what we want to do next is we want to play with all these equations. We can ask to calculate the total EMF of the cell, and we ask to calculate the terminal potential difference, and we ask to calculate the lost voltage. So these three formulas are very vital. Over in this place, you can make small letter b the subject of the formula, which should have E minus B, which is lost voltage. So apart from this, here I give us this, which is the lost voltage. You can also find your lost voltage this way based on how you are getting your question we want to play with. So let's quickly do some calculation under this.